or whoever was online, but she messaged the group.
Oh, that's right. Okay, so we are recording now, which is good because we're just starting the material. So what we're going to be doing is continuing from where we left off in chapter 1 or unit 1. Just a few other sort of housekeeping things to talk about. The sapling. Have people had trouble getting on sapling? Has that been working out okay for people? Working out all right? Good. That is all set and ready to go, ready for you guys to get online. And I mean, I could have showed you a little bit about sapling today, but obviously with no electricity, we can't do that.
Man,
yeah.
I have a question. Sorry, I didn't know when to butt in.
Yeah, anytime.
I have sapling for another course. So do I have to buy it for your course?
Send me a message. I forget the procedure, but if you already have sapling for a different course, there's something different you have to do.
Okay, thank you.
Just because I think we got special pricing for you guys in this course. And if you have it already for another course, there's something manual that has to be done there that we have to send in one by one. So yeah, if you already have sapling for a different course as well, send me an email once you have electricity and we'll figure something else out there. What else? I don't think I have too much else. The classroom capacity has been increased to 30. So we're going to increase the number of people that are registered to come to class. And I've rechecked just last night the poll that I put up. If you're with me here online and you wanted to actually be present in person some of the time or often or whatever, please go fill out that poll if you have not done so already. A few additional people have since Wednesday, so that's good. We have a schedule up until Monday already set. What I'm going to be doing is posting sort of an updated schedule for Wednesday and Friday next week. Sound good? Okay, so what we've been talking about is black, best contrast. How far here can I go? Right about here. I'm going to draw a line.
A little bit less. Can't see that.
Okay, that's okay. So that's my border. I'm not going to go past that.
Okay.
And on this side, I can go to about here. And then I'm not going to worry too much about being too high or too low. Okay, so I'm going to just draw a random molecule. No, we haven't. I don't want to get ahead of myself. Great. So here's a random molecule. All the lone pairs are drawn in there. This isn't any particular compound that I know of. It may look large and sprawling, and compared to the Lewis structures, you guys are probably used to drawing. This might seem kind of like something huge. Can online people see that okay? It's kind of there. I'll try to make it a little bit bigger next time. So this is actually considered a small molecule. So often in medicine, when people are designing new drugs, for example, one sort of class of drugs are called small molecule drugs. So most drugs that we commonly use, things like aspirin, ibuprofen, naproxen, you name it, are small molecules. Big molecules are often things with hundreds or thousands of atoms, and those are becoming very important in medicine today too. But this is a small molecule, even though it has lots of atoms, lots of central atoms. One thing that you guys need to be able to do or learn how to do is look at a structure like this and identify, hopefully almost immediately, what the hybridization is for every atom in it. Okay? So one thing that we know is that terminal atoms do not hybridize. Okay? So if you look at all of the atoms which are on the ends of chains, I'll circle them. First of all, Hydrogens are always terminal. Hydrogens are never hybridized. So they're always just one s orbital, so the only orbitals that hydrogens have, and that's it. The oxygen here is also a terminal atom, so it's not hybridized. Green means not hybridized. For the rest of them, they are all hybridized. If it's a central atom, it's going to be hybridized. And for an organic compound, typically your choices are sp, sp2, and sp3. And you look at the number of bonds or number of electron groups around each atom to determine what the hybridization is going to be. So let's take this nitrogen, for example. That nitrogen has how many single bonds? 3, yeah. This one. Yeah, it needs a hydrogen too. Sorry, thank you.
Excuse me, Matt.
Yeah.
Could we just get the people in the class to speak a little bit louder if they want, just so I can hear the questions, because I learn from them too.
Sounds good. If there's a question that comes up, again, I'll just repeat it.
Oh, cool. Thanks.
You can hear me okay?
Oh, absolutely.
Great. So this nitrogen that's right here has 3 single bonds, plus 0 double bonds, plus 0 triple bonds, plus 1 lone pair equals 4. So if there's 4 electron groups, that means it's sp3. How do you remember 4 is sp3? S is 1, P is 3, 1 plus 3 is 4. So if there's 4 electron groups, single bonds, double bonds, triple bonds, electron pairs, then 4 is sp3. Let's go to this carbon over here. That carbon has 2 single bonds. It has 1 double bond, has 0 triple bonds, it has 0 lone pairs. That equals 3. That means it's sp2. PPS, PPS, there's 3 things there. There's 3 electron groups, those match. So we know that carbon is sp2. Are there any other sp2 carbons in this molecule? Right here, good. So that one has 2 singles, 1 double, 0 triples, 0 lone pairs. So that one is sp3, sorry, sp2. This carbon here is also sp2. How about that carbon right there? Just sp. 1 single, 0 doubles, 1 triple, 0 lone pairs. So there's 2 groups there. That means it's sp. That's just 2 letters. 2 electron groups, 2 letters. There we go. This one here is also sp. And all the other carbons are this one, I believe that's it, are sp300. They'll have 4 single bonds. So that's something that we will have on probably an early test, is we'll give you a structure like this. We'll identify a few atoms and ask you guys to determine what the hybridization of those atoms. All right. Molecular shapes. So kind of continuing. All right, so we're going to continue with Lewis structures and talk about molecular shapes. So I'm going to take a molecule like carbon dioxide. And we want to draw its Lewis structure and determine what its molecular shape is. So what we do when we draw Lewis structures, we draw out the connectivity of the atoms. So we have carbon in the center, single bond to each of the atoms that are attached to it. We have 2 oxygens for CO2. And next, what we have to do is add up all of our electrons. So carbon has how many valence electrons? Do you remember that? 4, yeah, in the periodic table. Oxygen has how many? 6. And that is 12, 4 is 16. We have 16 valence electrons total in CO2. And from this, we subtract 4 for the 2 single bonds that we've already put in our structure. So 16 minus 4 is 12. We use those additional leftover valence electrons to fill up the octets of the outermost atoms. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we've used up now all of our electrons, and we have no more electrons we need to add or are able to add. That's it. Next, what we would want to do is look at our structure and see if all of our atoms have full octets or full outer shells. This is a better way to say it, because hydrogen doesn't get an octet. The outer oxygens are fine. They have 8. They have 2 here, plus 2, plus 2, plus 2. That's 8 total for that oxygen. Same for this oxygen, but how many valence electrons does this carbon have? It only has 4. 2 plus 2. So it needs 4 more electrons to get a full octet. So what we do is we go to adjacent atoms and pull, if an adjacent atom has an electron pair, we pull that down and use that to make a multiple bond. So let's give that a shot. Let's take 1 electron pair off that oxygen, make a multiple bond. Now this oxygen still has 8, but this one now has 6, so it's better. We can do the same on the other side. We have the structure here. So once you've gone through the procedure for drawing a Lewis structure, and you have your final completed structure done, with all of your formal charges assigned and everything else, what you can do with this structure now is assign what the shape is going to be. So what you do, and this gets a little bit different because we're counting electron pairs in multiple different ways as we're looking at different aspects of a molecule. But here, when you're determining shape, we want to determine electron groups the exact same way we did when we determined electron groups for hybridization. So for hybridization, remember we did number of electron groups is equal to single plus the number of double plus the number of triple plus the number of lone pair. So for the central carbon atom, what's the number of electron groups in CO2? There's 2. Yeah, we have 0 singles, we have 2 doubles, 0 triples, 0 lone pairs. So we have 2 electron groups. And 2 electron groups will always give you a shape that we call linear, with bond angles of 180 degrees. So we have a table that's in the notes, it's in the book, it's in the Lewis structure tutorial that I posted online on the side the whole time, which basically tells you, based on the number of electron groups, what the shape is, what the angle is. The hybridization you also get from this, hybridization is SP. That's a table you guys should just know. Okay, eventually you should be able to look at a molecule, maybe you can do this now. If there's 3 electron groups around the central atom, right in your head, think trigonal planar, just flat molecule, and be able to then take the next step. Okay, so being able to look at a chemical structure like this and almost instantly visualize in your head what the shape of that structure is going to be a very important and valuable skill in organic chemistry as we move forward. Because we're going to be looking more and more at larger molecules that have multiple atoms in it. And if you want to be able to look at the structure and kind of get a picture in your mind relatively quickly what that shape is. And one thing that we recommend for people, especially if you have trouble kind of visualizing 3-dimensional objects in your mind, is to get a model kit, and you can build these structures You can rotate the bonds. You can kind of feel what the structure looks like, feel what it looks like. I don't know if that makes any sense, but you get the idea, right? You can, yeah, you can, I don't know what I'm going to say there. We're good. We're going to move on. So I have a picture of the table right here. Make sure that you guys are good at or are able to take a structure once you've drawn it, calculate or figure out the number of electron groups around the central atom, each central atom in a bigger molecule, and determine the hybridization of each atom, like we already did, determine the bond angles and the shape as well, without looking at a table. Okay? You don't want to rely on that crutch every single time. Great. This is going to go, this example. I'm going to talk about something else that we do in organic chemistry. You might have seen this in first year as well, which is using what we call dashed and wedged bonds in order to identify the three-dimensional shape of a structure. So if you have a tetrahedral carbon atom, let's take a molecule of ethanol. That's ethanol. Its Lewis structure is going to look like this. I'm going to draw it here. Carbon. All right, so if I asked you to draw the Lewis structure, that would be great. I might then ask you to look at each atom and tell me if each atom is sp, sp2, sp3. All of them, the carbon, and the oxygen are all sp3 in this case. The shapes of all three of those angles, we would say, is tetrahedral. Well, we would say the oxygen maybe is bent because there's only two of those groups are atoms. But the shape, the shape, you count the electron pairs, for all of these, tetrahedral with bond angles of what? Good. 109.5 is the bond angle for tetrahedral. Now, the problem is the way I've drawn this structure does a bad job of representing what the shape is. All the angles, the way I've drawn it, look like they're 90, not 109.5. It also looks flat. This molecule is not flat, three-dimensional tetrahedral kind of shape for each atom. So we have sort of techniques, a number of techniques, to say what the three-dimensional structure of something like this is using just the two dimensions of the blackboard. So if I was to draw this properly with a three-dimensional structure using what we call hashed and wedged bonds, it would look like this over here. Try to make this. All right, does that look sort of clear, online people? Doesn't look terrible, does it? See my giant face?
I think
okay. So what this is showing here is if you see one of these sort of thick, triangular, kind of wedge-shaped bonds, that means whatever's on the other side, on the fat end of that wedge, is not actually flat in the board, but it's coming out towards us. So that hydrogen would be kind of out like this. And if it's got these dotted hashed bonds, it's going backwards into the plane of the board. Okay. So we see this carbon has one hydrogen that's in the plane of the board. We just use a regular line. We have one that's in front of the board, which is this hydrogen, and one that's in behind the board, which is that hydrogen. So it kind of gives you a three-dimensional perspective of a structure like this. And as we get deeper into reactivity and things like that, these shapes become increasingly important. All right. Condensed structural formulas are next. So these are different ways of representing the molecule. All three of these representations are the same thing. If you're an experienced chemist, I could show you any one of these three images, and you should have the same sort of idea in your mind. Same picture, same compound. You might start thinking about the properties of the molecule, right? This is the compound that's in beer and alcohol and, you know, that kind of stuff. It's the liquid, boils at 79 degrees Celsius, dissolves in water, et cetera, et cetera. Notice, though, this way that I've drawn it up here, I didn't show any bonds. I didn't show any lone pairs. What's the advantage of this particular way of writing it? Well, it took me like 2 seconds. To draw out every single structure like this has maximum information, but it takes a long time to draw out. Especially think about when organic chemistry kind of started, like 100 years ago. People didn't have computers to draw fancy structures like we do today. So these were very hard to publish. And so what people wanted was a sort of a shorthand way of identifying chemical structures. And that's what they did. So they wrote them out like this. This could be easily typed. And this means there's a CH3 group, which is like a C with 3 hydrogens, attached to a CH2, so it's a CH2, attached to an OH. And we call these condensed structural formulas. So the advantage of these is that they are, well, easy to type, easy to kind of identify. So if you look at something like, here's an example. I already made a problem. C. This is a relatively simple molecule. It's small, doesn't have that many carbons. That's kind of a mess to look at, right? Even for something that's small, there's so many atoms and so many bonds that are drawn in that it's difficult to just kind of look at it and see what the structure is. Especially if you're writing say a paper or a lab report or something, and you have a lot of structures, you could fill up pages and pages and pages of just pictures like this with atoms. And it's almost incomprehensible to look at a big structure in this kind of a format and learn information about it. So the condensed structural version of that one would be like CH3, okay? And there's a CH2, then there's a CH, and then there's a branch that goes down here of a CH3. We would just go CH3, 2. Actually, we could put, because there's 2 CH3s that are there. So that's shorter, it's easy to type. You see these quite often in books and literature and things like that as a shorthand way of writing a structure like that. Although these become pretty bad too if you have like 10 carbons or more. These get really ugly looking too. If you have interesting structural features like you have rings or things like that, these become very difficult to write out clearly and properly. So they're best used for small molecules. By small molecules, I mean definitely like fewer than 10 central atoms. We have a better way though. We have a better way, and we call this bond line structures. What bond line structures are is it's a method of writing out a structure like this. But what we do is we don't draw in the C's. We just assume that if there's no atom symbol drawn in the Lewis structure, that it's a C. We also don't draw in lone pairs, and we don't draw in hydrogens that are bonded to carbon. We just assume all of the carbons have enough hydrogens to make a full octet. We kind of trim off all of the crap that's in this structure into something that's simpler and easy to see, easy to instantly recognize what it is. Because there's a lot of redundant information here. We know that carbon, if you left those hydrogens out, you know that there's got to be 3 there. Because you can't just have a carbon dangling off the end with no hydrogen. That's not a stable molecule. Or if you did lose some hydrogens there, you would have either lone pairs or formal charges or something like that, we would include. So the shorthand version of this, if we get rid of the carbon symbols, we get rid of the hydrogen symbols if they're bonded to carbon, becomes just this. We have 1, 2, 3, 4 in a row at the top. 1, 2, 3, 4. And I guess we have a carbon off there as well. Lizzie, do you have a question?
Yeah, this is the name of that.
This particular molecule? The question was, what's the name of this molecule? So there's different rules for naming them, but the accepted ones in the chemistry community are called IUPAC rules. So the name for that is what you do is find the longest carbon chain, which in this case is 1, 2, 3, 4, which gives it the name butane. And then the side chain there is a methyl. So it's 2, because if you count carbon 1, 2, 3, 4, it's 2-methyl butane. All right, so we've simplified the structure to just this guy up here. That's the bond line structure. Yes?
Does it already start from other direction?
Doesn't matter at all.
Okay.
So if we started from the other side and started with this carbon and drew something like that instead, flipped it around, flipped upside down, rotated, it doesn't matter. These are all the same thing. Yeah. There's no formalism about where you have to start or anything like that. Draw however you like. So this is much smaller, much cleaner. It's easier to look at it immediately and kind of grasp what we're looking at here. You'd have to be able to look at it though, and every little corner or end is a carbon. And you have to be able in your mind rebuild it and put how many hydrogens ought to be on each position back. So this carbon here, for example, there's 2 bonds that are shown to that carbon. It's got to have 4 bonds, or it's got to have 4 pairs of electrons. So there's got to be 2 hydrogens there. And this becomes very easy to see. It might be like a lot of figuring at first, but eventually you'll just look at the structure and be like, oh, that's a CH. Oh, that's a CH3. I'm going to give you another example and show you why chemists love using these structures. This is going to be a molecule that probably everybody here has derived some benefit from. Again, a nice little small molecule. Not that many atoms. Some more room over here. There. So that molecule is a common over-the-counter drug. It's Ibuprofen, which is Advil. And the way I've drawn it there, it looks big, gangly, atoms sticking out everywhere, single bonds, double bonds, just atoms. Like it's hard to look at that and like in your mind create a picture of the shape of this molecule. So if we make the shorthand version, if we make the bond line structure of this, it just looks like this. I hope you agree with me, that's a lot smaller, a lot cleaner, a lot easier to tell if you're looking at this molecule where the action is. And I guess that's part of it too. In organic chemistry, carbons and hydrogens are usually the boring parts. Usually it's the other parts of the molecule that give it what we call its function. We actually call them functional groups. So we have this structure here. The name of this compound, by the way, comes from its structure. This group that you see right here is called an isobutyl group. That's the IBU is isobutyl. The pro comes from this group right here, which is called propionic acid. And then the group that's in the middle is the benzene ring. We call those phenyl rings. So it's ibuprofen for phenyl in the middle. So often the actual compound name, that's not an IUPAC name, that's not an official, standardized, it's a trade name, but often they're based on the structures as well. Notice in our structure here, I didn't draw any lone pairs. We don't put lone pairs in bond line structures. We assume there's enough lone pairs in there to fill the octets of what's there. But I did draw that hydrogen, didn't I? I told you before we don't put hydrogens in, right? Not exactly. I said we don't put hydrogens in if they're bonded to carbon. We have to draw hydrogens if they're bonded to something other than carbon. Okay. So we draw the hydrogen in this example because it's bonded to an oxygen. Yes, Lizzie. This one here? Yes, the question is, what is this group called? It's not an official, it's not an IUPAC name either, but isobutyl. Butyl means 4 carbons, so there's 1, 2, 3, 4. And iso is that arrangement. Yes. Small molecule, yes. The question is this big or small? This is definitely small. Yeah. Big is like a protein or an enzyme or like thousands and thousands of atoms. And there's lots of drugs that are like that now. Like, what are they called? Antibodies. Like you can do antibody therapy and things like that. Those would be drugs with giant molecules. Like it would take you all day and all these boards to draw even part of one of them. So these are nice little small guys. That's where we like to start in organic chemistry because start small. No. So the question is, do small molecules versus big molecules have different physiological effects? Well, they have different effects, but not stronger effects. So small molecules, they operate by a different pathway. Small molecules would operate by fitting into the active site of a specific enzyme or receptor or something like that in the body, and often either triggering a biological response or suppressing often a biological response. And so these small molecules often, in many cases, would mimic a molecule that your body makes, but maybe its effect is 10 times stronger. So a good example is sucralose. Sucralose is an artificial sweetener. It's very similar structurally to sucrose. And when you get it in your mouth, it goes into your sweet receptors in your tongue. Your body can't tell the difference between that and sucrose, but the thing is it sticks to that receptor much more strongly than sucrose does. So the effect on your body physiologically is the same as sugar. The taste is the same, but its effect is like 200 times stronger. So we can change structures slightly. All right, we're doing great here. I want to do hybridization on this beast while we're here. Is there any sp carbons? Okay, there's no sps because there's no carbon-carbon triple bonds. There's no carbons. The carbon has 2 double bonds, like in CO2, that'll also make it sp. We don't have that in this case either. What about sp2? Are there any sp2 carbons?
Yeah.
How many?
Six.
7. I'm going to circle all the sp2s. 1, 2, 3, 4, 5, 6, 7. Can online people see what I circled?
Kinda.
Yes.
Yeah, I see it. Yeah, I can see him.
So all of those have one double bond and two singles. A bunch of these, I didn't draw the single bond because it's a hydrogen. We don't draw them in bond line structures. What are the remaining carbons? They're not sp, they're sp3. Okay, so if carbons, and you'll recognize this shorthand quick. If carbons have all single bonds, it's sp3. So all of these carbons here and this one here, all the bonds to it are single bonds, sp3. Okay. All right, the next thing I wanted to talk about, how are we for time, by the way?
There's like 15 minutes.
Okay, great. We're doing great. It's faster now. I'm not talking about everything on my slides, but I'm talking about the important stuff. So another thing that's important in organic chemistry are compounds that have the same molecular formula, but are different structures. So the same atoms, but they're put together in different ways, and you end up getting structures that have different properties, different everything. So I'm going to go back to this example, which is C2. I think black's probably going to be easier for people to see if you're online. Switch away from green. C2H6O. So in first year chem, we often refer to compounds by their formula like this. We would calculate things like molar mass and balance equations and convert moles to products and percent yields, all these sorts of things. Organic chemistry, we don't really do that as much. I mean, we do definitely when you're in the lab. You need to know the moles, you need to measure the right amount of grams and all that kind of stuff. But in the course, we don't really do those calculations. Okay? We assume that you're good at that already after having done it many times in first year. But this, to an organic chemist, doesn't tell us a whole lot about what it is that we're dealing with. Because we can have two compounds, we can have that molecule, or we can have that molecule. Both of those molecules are C2H6O. Okay, that's a CH3, CH2OH, or CH3O, CH3. They have different names. This is ethanol. This is dimethyl ether, it's called. This has a boiling point of like 80 degrees, 79 degrees Celsius. This has a boiling point of like -30 degrees Celsius, like 100-degree difference in boiling point. Why do you think this one's so much higher? It's got hydrogen bonding because it has an OH. This one doesn't. It's very low boiling. Yeah, so ethanol also has quite obvious biological effects if you consume it. This doesn't really have much in the terms of biological effects. So we would call these two things isomers. They're different molecules that have the same molecular formula. And we're going to be talking about isomers quite a bit in this course. Some isomers are very similar in their properties. Some, like you see here, are very different. In fact, we're going to be breaking isomers down into a bunch of subtypes. These two we would call constitutional isomers, which means they're different in structure, but the order in which the atoms are connected are fundamentally different. We have other kinds of isomers that we'll deal with later called stereoisomers, which means they're bonded together in the same arrangement, but the three-dimensional shapes are different. We'll see those examples as well. I'll give you an example right now. Why not? You have these two molecules, same order. It's a CH3, CH, CH, CH3. This one is CH3, CH, CH, CH3. Okay. So the order in which the atoms are bonded, we say the connectivity is the same between these two molecules, but they have different shapes. This one kind of goes like that, and this one goes like that. Okay. We use the terms typically trans for something like this. The word trans means across. So if you look at that double bond, those two groups are across from each other. Same when we use trans Canada, right? Goes across Canada. This one we would call cis. Cis means same or together. So on this side, the two groups are on the same side of that double bond. So we say this one cis. We actually have a nomenclature for these that we're going to deal with later. It's called EZ nomenclature. It's called it's IUPAC. IUPAC is the International Union of Pure and Applied Chemistry. What that really means is an international organization where people get together and make decisions on sort of worldwide standards for how we do things in chemistry, in terms of naming things and measuring things, units, all these kinds of things. And it's very important for people to easily communicate with each other, that we all use the same language. And yeah, there's an argument, just go to IUPAC, see what they say. The argument over. Go with whatever they want. Okay, so I'm going to teach you one idea, and this one idea is probably 50% of what you need to know for this course, or underlies 50% of what you need to know for this course. And it's simple. Charge is bad. Charge is bad. So what that means is if you have a molecule that has a formal charge, ideally, it would like to change its situation so it doesn't have that formal charge anymore. Either by reaction, by decomposing, by some other process like that. Now, sometimes you have molecules that are stable, that have charges, and that can't really be helped, right? Like sodium chloride, nothing more stable than salt, and it's got charges. Okay, that's fine. But for organic compounds, they typically love to be neutral if they can. If there is charge, then they'd like to react to get rid of that charge somehow. They can. That charge is worst when it's all piled into one spot. If they could take that charge and spread it out over a bunch of atoms, that makes that charge less of a problem, and it makes that molecule much more stable. And so many properties and reactivities of molecules are just dictated by that one idea. That charge, if it's all concentrated in one place, makes the molecule like reactive or unstable. Or if it's spread out, that's going to be better for that molecule. It's going to make that molecule more stable. So intermolecular forces. We know when you have charge built up in one spot or not another spot in a molecule, that is responsible for intermolecular forces. That's why we have hydrogen bonding, why we have dipoles, polar bonds, you know, all those sorts of things. We also know acids and bases typically involve forming charge or neutralizing charge. So acidity and basicity, we can say, is a phenomenon of charge is bad too, right? Another idea, which we're going to talk about later, is called nucleophilicity and electrophilicity. And this comes back to an idea that you learn in first year, which is Lewis acids and Lewis bases. We use those a lot in organic. We just give them different names. We call them nucleophiles, electrophiles. All right, so the last kind of topic, and this is a biggie in this unit, is the idea of resonant structures. Resonant structures are this add-on unit that we always do with Lewis structures that throws a lot of people. And I know students will march through the Lewis structures, they'll be fine, Lewis, formal charges, whatever, they can draw Lewis structures. But when it comes to resonance, you know, a certain chunk of students are just like, I'll just hope there's not a resonance question on this next test and move forward, right? Well, you can't do that here. We got to come back to resonance, and I want people to understand resonance really well, because what resonance does is it takes a charge and spreads it over multiple atoms. Organic chemistry, this is like super important, because in organic and chemistry, we are typically dealing with lots of atoms compared to first year where you have a single center and then a few things around it. So whether a molecule is reactive or not in organic chemistry may come down to, does it have resonant structures or not? Okay. So I'm going to give you an example. I keep coming back to ethanol, not just because it's Friday. But here's ethanol. Ethanol, it has an OH, and ethanol can act as an acid. What does it mean it can act as an acid? What do acids do? Yeah, they donate H+.
Neutralize a base.
Yeah. So this can react with water to establish an equilibrium, which makes O- plus H3O+. Now, is ethanol a strong acid? No, it's a super weak acid, barely acidic at all. But so we put this equilibrium arrow to show that it's not 100% to the right. If it was 100% to the right, we'd have a strong acid. Because this is an equilibrium, we have a K. We put a little A because it's an acid, Ka. And what we can actually do is establish something called a pKa, which is the minus log of Ka, which we use much more commonly in organic chemistry because the acidities of organic compounds is quite variable. The Ka for this is like 10 to the minus 16, which means the pKa is roughly 16 for ethanol. That's a super small number, right? 10 to the minus 16. That means that if you mix ethanol and water, a super, super tiny fraction is going to dissociate into O- and H3O+. Okay? For all intents and purposes, we might say that this is not an acid because its pKa is so high, Ka is such a small number that the acidity of OH is almost not important. Now I'm going to look at another molecule which is very closely structurally related to ethanol. In fact, if you have a bottle of wine that you open and you leave it on the counter too long, this is formed from the alcohol in there. What's the same? But no, we're going to put an oxygen here. What molecule is this? Ethanoic acid is the IUPAC name. That's right. The common name for this is acetic acid. Acetic acid is another name for vinegar. And so if you take wine, which has ethanol, and leave it out and it oxidizes, it becomes this. Okay? That's how vinegar is often made. This is an acid too. In fact, it's called acetic acid. Okay, so what's the pKa for this thing? It's like a super common example in first year when you do acid-base chemistry. I don't expect you to memorize the Ka or the pKa of this thing. I happen to, just because I've taught it so many years. It's 4.73. That's a little bit lower than 16. In fact, it's what, 11 orders of magnitude lower? So this is 11 orders of magnitude, one with 11 zeros after it, that many times more acidic than ethanol. So there's a super huge difference in acidity between these two molecules, despite them having, at least on the surface, apparently pretty similar structures. Let's get rid of this part here. I'm going to show you why. Why there's such a difference between these two, and how if you skipped in your mind the whole part on resonant structures, you wouldn't be able to justify it. This becomes, I'm going to draw all the lone pairs here. We call this ethoxide. This guy down here, though, like that. This one have a resonant structure. Yes, or I wouldn't ask. The resonant structure of this So for everybody that's looking at this and saying, you just took the same molecule and you flipped it over. No, I didn't. This is not, I didn't touch any atoms. All I did is I moved electrons. So what I did is I took electrons from this oxygen, move them here to make a double bond, move these electrons up there. All right, my fingers are now covered in ink. That's not blood. I hope no. So what that means is this molecule in the real world isn't this, it isn't this. It's a 50-50 blend of those two structures. So I can go over to here. So I'm going to use this part of the board. That means the real structure looks something like this, where it's 0.5 negative, 0.5 negative. So that minus charge is equally split over the two oxygens. Each of those oxygens has minus 1/2 of a charge. Neither of them have a full -1. It's not like you have this structure and they're whipping back and forth. It's not these two, you know, first it's this, then it's this. It's not quickly moving. It's always that. And this is a hard concept for people because you learn Lewis structures and all of the electrons are these little round dots, or they're in a bond where we think of them, they're fixed in location between these two atoms. And we forget sort of the first chapters you do in first year chem, when you look at electrons and they're not hard little dots. They're, according to quantum mechanics, you can't treat them as little tiny dots that are, you know, orbiting the nucleus. They are diffuse, they're spread out. You can spread a single electron out over several atoms. And you can smear that charge. Like, think about electrons instead as being like a big poofy cloud. Or like, and you can pull that and stretch it and make it extend over an entire molecule if you want. And that's what we're doing here. By drawing these two resonance structures, this is sort of the best representation we have using the rules of Lewis structures to show that there's molecules that exist like this, where charge isn't in one place or another place, it's evenly spread over multiple locations. So that gives this compound great stability because charge is bad. Charge is bad here, but it's stuck in one atom. It's stuck there, it's the only place it can be. This doesn't want to form because charge is bad. This one, charge still bad, but it's spread out over more atoms, which makes this dramatically more stable than this. So if this anion is more stable, it forms easy. That makes the acid a stronger acid. It easily gives up that proton because it can make this relatively happy anion. And if you look at all of our strong acids pretty well, most of them give anions that have resonance structures. So what are our strong acids? HCl, HNO3, HBr, H2SO4, HCl, HBr, HI is on that list as well. Pick up power. Either that or the battery died on this thing. Anything else? There's one more that we don't often talk about. Perchloric acid, HClO4. All of those give anions that have resonance structures. Nitric acid makes nitrate, and nitrate has this Lewis structure. And you can have the double bond here or here. There's 3 versions of that. H2SO4 as well, you lose 1 hydrogen, you have HSO4 minus. That negative charge is spread equally over 3 atoms. Busy. It's 9:31. Okay. Thank you very much. Thanks for bearing with me during another technology fail, although this one is not my fault. Yeah, this is kind of nice because you guys don't have to rush for the next class. I can keep you late every day. No, I'm just kidding. I won't do that. Thanks to everybody who met me online. And I'm supposed to be having office hours now. I can do that. Give me like 5 minutes to go to my office. And office hours are through Teams as well. So if you have any follow-up questions or anything like that, we can chat there.